50 years of mapping led to a perception of the moon as a static environment, a quiet, frozen museum piece floating 250,000 miles away. In April 2026, the Artemis II mission challenged that assumption, sending 4 astronauts further from Earth than any humans in history. This was a scouting run. The goal was to validate our deep space physics and engineering models before we attempted to build permanent lunar habitats. At the moment the crew looked out the window at the lunar far side, it became clear that our foundational baseline models were incomplete. As Orion crossed behind the lunar bulk, the moon's mass severed the radio line of sight with Earth, triggering a 40-minute communications blackout. Reaching a record distance of 252,756 miles, all telemetry flatlined, leaving the 4 astronauts in absolute isolation. Inside the capsule, the atmosphere changed. The mission was no longer a routine scientific survey. It had transitioned into a survival exercise. During these minutes of silence, the crew observed a world that was active, unpredictable, and much more hostile than our records suggested. While passing over the lunar night, the astronauts saw 6 distinct, bright flashes of light erect across the surface in less than an hour. Earth's atmosphere burns up debris through friction, but on the moon, a pebble-sized rock retains its full momentum, striking the ground at 30 kilometers per second. This instantly converts kinetic energy into thermal energy, vaporizing the rock and soil into a cloud of glowing plasma. We spent decades viewing the moon as an ancient, quiet graveyard. These flashes suggest an environment undergoing constant, high-velocity bombardment. Any future infrastructure on the surface will be deployed into a territory where these impacts are a near-hourly occurrence. The geology wasn't the only surprise. As Orion reached its closest point, it experienced an unexplained velocity increase. A 0.7 millimeter per second flyby anomaly revealed a gap in our gravitational math. Outside the protection of Earth's magnetic field, the crew also faced the raw output of the Sun and high-energy galactic cosmic rays. Radiation sensors inside the capsule logged exposure levels 18% higher than pre-flight scientific models had projected. To measure damage, the crew used bone marrow chips. They showed high-energy particles passing straight through the hull to intersect with cellular structures. The astronauts actually saw this radiation, reporting sharp flashes of light with their eyes closed as particles physically struck their retinas. These deviations in orbital velocity and radiation exposure show that our baselines for deep space physics and biological survivability are currently misaligned with reality. Automated cameras miss subtle details. The crew identified silvery and greenish tints in the surrounding ejecta blankets. Mineral variations our orbital probes failed to record. However, human vision has its own limits in a vacuum. On Earth, we rely on atmospheric haze to judge distance, but on the moon, that depth perception completely breaks down. Without an atmosphere to scatter sunlight, lunar shadows manifest as ink-black voids, defined by sharp edges where the light simply stops. This creates a critical hazard for future landings in the South Pole Aitken Basin, where massive impact structures create zones of absolute darkness. In these regions, human eyes and automated sensors cannot distinguish between a shallow dip and a mile-steep drop. Even with advanced sensors and artificial intelligence, human visual processing remains a flawed but necessary instrument for navigating the lunar environment. While the moon provided unexpected challenges, the crew also had to contend with a documented flaw in their own spacecraft's protective shell. After the Artemis I test flight, engineers found that the AV coat heat shield had failed. The outer layer had hardened too quickly, trapping gas pressure as the shield began to break down during re-entry. This trapped pressure literally blew chunks of the shield off into space, leaving the capsule hull exposed to extreme temperatures. To keep the Artemis II crew from burning up at Mach 33, Mission Control had to utilize a shallow loft trajectory, a maneuver designed to minimize stress on the compromised shield. This mechanical failure shows that even our most rigorous engineering solutions operate with narrow margins when exposed to the conditions of deep space. The Artemis II mission shifted our perspective, revealing the moon as an unpredictable, high-energy wilderness. The data collected from this flight is now being used to redefine the requirements for the Artemis III landing and the construction of the Lunar Gateway Station. The moon is the mandatory laboratory where we must solve these kinetic and radioactive anomalies before we can attempt a journey to Mars. Surviving the solar system begins with looking at the evidence, discarding our old assumptions, and admitting how much we still have to learn about the void.